Hello, my name is Michael Mathis, and I'm here to describe a theory called oscillation and deformation theory, which I developed to describe inertia and momentum. The theory proposes basically that that an object's resistance to movement is not the same as an object's movement, although they are related. So when an object resists stopping from moving, momentum, it is not the same as an object resisting moving. They are related, though. The theory basically proposes that a wave, or two types of waves actually, move through the object and create a outward motion. And basically, the waves cause the object to have different mass on each side periodically, so the direction that is traveling would be the y-axis. And so on the y-axis, it has differing masses on each side periodically due to a compression wave. So the compression wave travels through the object up and down, and it when it's at the top, another wave, which is if the object was circular, will deform the wave and elongate it along the x-axis and the y-axis. So it elongates it on both axes. I'll show you. I have a little chart here that I'll show you. Okay. Basically, what I've done is I've drawn out several x and y axes to show the represent the object. Okay, this is number one. Here is these numbers here are the phases broken up into 8 different sections. So a phase of a cycle. So the top row is the deformation cycle, and the bottom numbers to 8, 1 through 8, is the compression cycle. And these are the phases of the cycle. And you can see here after 8, 1 starts again for the deformation cycle, and after 8 here, 1 starts again for the compression cycle. Okay, here on this graph, the first one is not affected at all. It's just an object at rest in space. Okay, number 2, this one, the second one here, is actually the first part of an acceleration on the object, and it shows the y-axis compressing and the x-axis elongating. Okay, and that's the deformation. And it shows the beginning of a compression wave here. A little bit of compression at the bottom here, and you can see this little dot with these dots here at the bottom. That's representing the compression wave. And you can see here, this is the number 3 phase of the deformation standing wave. And you can see again the x-axis has elongated further, and the y-axis has compressed further. As the object starts to push away from the, so if the impact was here, the object starts to push away from the two objects, starts to reform and push away from each other. The deformation is starting to rebalance itself to an equilibrium, and so the y-axis is elongating again, and the x-axis is shortening. And you can see that the compression wave has not started moving yet, and that's because the two objects are still touching, and the compression wave won't start moving until the objects actually stop touching each other. So here at this is, you can see this is where the compression wave cycle starts. This is the first phase, and it actually, this is where it'll start moving. And you can see that the x and y axes are equal in this instance. And it is the fifth cycle, the fifth phase of the deformation cycle. Okay, you can see now at the sixth phase of the deformation cycle, the y-axis has elongated now, and the x-axis has shorted, compressed. And the compression wave has started to move. It's about moved a quarter through the y-axis. So now the x-axis, excuse me, has fully compressed, and the y-axis has fully expanded, elongated. And you can tell that the compression wave has now moved past the y-axis, just past it. And you can tell the process continues till here, as this is actually when the I should explain this a little further. As the x-axis is compressed here, the y-axis is elongated completely. It's going to start to go back to an equilibrium, to normal size, and as it does that, both parts are going to be pulling on each other, so that each sides are going to be pulling on each other, and so the compression wave causes more mass to be on the top of the object on the y-axis. You can kind of see down here how this kind of works. This is another kind of just a little depiction showing how it works. This is the compression here. This is the equilibrium. And this is the elongation. So you can see as the object elongates here, it has less mass on the top than it does on the bottom. So the top actually moves further. It moves further distance in space than the bottom does. Now, when it comes back together, the compression wave will actually move to the top, as you can see up here. And when it pulls back together, the bottom half will actually move further in space. So it's constantly kind of like pulling and pushing itself through space as this compression wave oscillates back and forth from the top to bottom, 180 degrees out of phase with the deformation wave, the standing wave. And it causes the waves to be in different positions all the time, so that when the deformation is kind of pulling back together, that the compression wave is always on the top, so it's always pulling the bottom further up. And when it's pushing away, the compression wave is always on the bottom, so it's always pushing the top further up, so kind of like reaching up and then crawling through space. So it kind of like moves like this. So that's how the kind of motion that it has. And you can see here, down here, this is the this is supposed to be the start of the deformation wave here. This is the start of the oscillation wave, which is a compression wave, and this is a standing wave. You can see that they are 180 degrees out of phase. And this just kind of shows a very more detailed depiction of what is happening. So you can see as the wave is starting to compress here, the y-axis is compressing, the compression wave is on the top, so as to pull the bottom half up. After right when it's compressed completely, the compression wave, when the y-axis is compressed completely, the compression wave has moved just beneath the x-axis to be on the other half, so that when it starts to expand again, as you see over here in phase 4, that it is on the other half, and it pushes that half up further. and it does so until it completely expands. So this is the this is the step 4 complete expansion of the y-axis, and you can see it's just below it's midway through the y-axis. So it's a quarter through the y-axis and it's midway through on the bottom half. And after it's completely expanded, it has just passed over the x-axis, so that when it starts to compress again, that it is on the top half, and the bottom half will move up again. And so this is the just the depiction and graph that I have made to try to show how this this works. If you have any questions about the workings or any other writings that I have, just please send me a message. Another thing I kind of was wanting to mention, that there are equations that I have been working on that describe how the object loses volume as it accelerates. So as a force accelerates the object, it has to continue to push against the molecules in it, which kind of compress those molecules like a spring. And there's no way for that compression to be relieved once that acceleration leaves. So they constantly have this this compression. That compression will move, and that's actually where you get the compression wave, is from these molecules. And the amount of compression is relative to the amount of speed that the object has, and the amount of deformation as well. I also like to mention that one reason I believe that this has not been observed is because if you were traveling the same speed as this object trying to observe this phenomenon, you would have the same waves moving through you. And so I'm not sure that they would be the exact same waves, since you may be made of different material than the object you're observing. But there will still be waves moving through you as well as there are through the object you're observing. So the only way to really observe it that I could think of would be to observe it from a still point as you observe an object moving by. Another thing is that Einstein's equation actually mentioned an object gaining mass. I'm not really sure why he said that as it accelerates, but I thought that it was interesting that my equation, the equations I was working on, predicted that the object would lose density, lose volume and gain density as it accelerated, and that it would not be able to move past a certain point of speed because it would become too dense, so that it would not be able to move any further. It would not be able to compress anymore, and therefore it would not be able to accelerate anymore. So anyway, just some interesting things that I had thought of, and I hope that if you have any questions, that you will send me a message or comment, and thank you for watching.